Well, that is all now for the molten welding, but we have the solid state welding. So I'd like to dispose of the solid state welding first. And this is always a lot of fun for me because I know how to do this. You know, you people don't know how lucky you can be if you don't happen to have been born in a city or raised in a city. I was born and raised in the dismal swamp of Virginia, and so I had to live like in last century in my childhood. I didn't have to, but I did. In the summertime, I was moved to a farm, and on the farm, the man that operated it, my cousin, did all sorts of things. He was a blacksmith. He was a farrier. There's a difference between the two. He was a wheelwright. He was an everything. And so as a boy, I watched him do a lot of things that I thought were interesting, and I learned to do some of them. But let me describe what this man, this blacksmith, did. And I saw it as a young man, and I have seen it since, and I can do it myself. When someone brought to him, say, an article that was broken, a piece of steel. Now, the piece of steel that was broken in two pieces, I'll just represent with my arms and my hands. The first thing he would do would be to chamfer the edges of them, to hammer them out, so that when he put them together, they would touch at a point, all right? And what he's going to do now is he's going to cause these two surfaces to be welded together, plastically welded together. He's not going to melt them. So he takes the two pieces of steel, he puts them in his little forge, he cranks the forge up, he gets the material incandescent. This means it's going to be up at temperatures of 1800 degrees, 2000 degrees, very, very hot. At that temperature, the material is going to be oxidizing like mad. So when he takes it out, he'll have two oxide-covered pieces of material. If you put them together, then, and he tried to weld them, he would incorporate iron oxide in his weld. He would have a non-metallic inclusion that has zero strength, and he may have stuck them together. It may look good, but he would not have performed a good weld. So what he really needs to do is he needs to get rid of that iron oxide. So when he pulls it out of the fire, the first thing he does is to stick these incandescent pieces into some borax glass. The borax glass combines with the iron oxide to make a slag that is very fluid. And now when he puts the two pieces together and they touch at that point, it exudes the borax glass on both sides, and he has a nascent metal to nascent metal point contact. When he does this, when he puts this borax glass on it, the borax glass protects the rest of the iron from oxidizing. No oxygen can get to it. And what is the stress that he will get if he put them together at just this point contact and hits it with a hammer? What do you think the stress would be if you put two surfaces together that were spherical and just pushed on them with your finger? What's the stress at the point of contact? Infinite, right? Because the cross-sectional area is zero, approximately zero. So he knows that if he hits this thing with a hammer, he doesn't know anything about stress and strain, but he knows if he hits it with a hammer, two things are going to happen. He's going to collapse it at that point. It's going to flow because the stress is infinite. He's going to bring the two masses of iron together into nascent contact. And at this temperature, if he brings those two surfaces together in nascent contact, the metal atoms just bond together, and he has a plastic weld. As he continues to hammer the material, it's still hot, it flows easily, he continually exudes this slag from the side and continually brings all of the metal into nascent contact, and when he's through, has this beautiful plate that bar that he's welded together. He's never melted the material, he's only beat it with a hammer, right? It's called plastic welding. Now that sounds pretty straightforward, I think, but the fact of the matter is you can do that cold as well. Let's see if you don't already know this. How about if you were to take, say, a piece of lead and a piece of brass and rub the two pieces together and then look at them. Or let's say a piece of lead and a piece of copper would be more visible, and you rub them together. What would you expect to see in your hand? You'd expect to see, on the copper, you'd expect to see a streak of the lead on there, right? So you have plated over onto the piece of copper some of the lead. You have had a galling. You've had a little micro welding. So actually, if we were to take two pieces of cold material, put them together, even though they had an oxide film on them, and increase the surface area. So we break the oxide film and move the little oxide particles far, far apart, at the same time holding the surfaces together so no more oxygen can get in, and bringing them in nascent contact, then all of a sudden we're going to find out the stuff is welded together. And so, for instance, we get into this nice little metallurgical field. It has to do with joining that we don't pay much attention to, but really talks to us. Suppose you go buy a piece of jewelry for your boyfriend or your girlfriend or something, and you say, hey, I like that, whatever it is, that little trinket, and it says on it, it's a 1/10 GF 14K. And the guy says it's 14 karat gold. And you look at it, it says 14 karat gold. Nobody's going to lie about that, so you buy it. It's 14 karat gold. But what about all the rest of that garbage that was written on, right? 1/10. Now, what that really means is that 1/10 of this material is going to be gold filled. It's going to be gold filled or gold rolled. And that material that is 1/10 of all of that is only going to be 14 carats. So that's going to be 14/24 gold, right? So you don't get much. Oh, but it does a lot of good. It's all on the surface, and it performs perfectly. How did they get that gold on the surface of a piece of, let's say, high-carbon steel, if they want it? Or let's say on a piece of brass or a piece of bronze. How do they make your eyeglasses if they're going to be a piece of brass? The little stem on your eyeglass, so when it goes over your ear and you perspire and get your body fluids on, it doesn't make a green streak on the side of your head, right? A good way is to coat it with gold. Well, what they'll do is they'll take a cylinder of the base material, the springy material, the strength material, and they fit over top of it. It may be a bar, say 2 or 3 inches in diameter, and they'll put a sleeve over top of it of gold. And they take that particular material and begin to put it through the rolling mill, shaped rolling mills. And they keep on reducing it in size, smaller and smaller and smaller and smaller, and they're just making wires. But they're stretching out the gold, and they're stretching out the steel. At the same time, they're bringing them into nascent contact, and it just welds. It's a beautiful weld. It's a cold welding job. Now, I'm going to tell you something about welding that we'll talk about a little bit tomorrow, but there's a method of coating steel to make it corrosion resistant, where we use zinc and put it on the surface. Actually, there's a process for coating zinc onto steel called mechanical plating or peen plating. And what you do is take, say, fasteners. Let's suppose you have nails and you want to zinc coat the nails. You throw a bunch of nails into a ball mill. You throw a bunch of zinc into the ball mill. You put water in the ball mill. And then you put this special material in the ball mill that's called a promoter. The promoter happens to be a weak organic acid that is philic to the metal. That means it wants to wet the metal. So it coats all the metal particles. The nails, the zinc powder that you put in there, everything is coated. And it's like an oil, and it keeps oxygen from getting into the system. And you tumble it in the water in the mill, and you bring 2 pieces of zinc together, and then on top of them, another bunch of nails, hit it and flatten it out. Increases the surface area. The spheroidal powders, they just weld together. They also weld to the nail. So you run the ball mill for 15 or 20 minutes, open it up, pour out a clear fluid, because all the zinc will be on the nails, and these nails then are zinc coated by cold welding. Millions and millions and millions of cold weld points. So the business of plastic welding did not leave us with the blacksmith. It's still with us today. It's a perfectly good system of, say, making a weld junction in an aluminum wire by just having a little wraparound tool that was invented by GE, I believe, so that you can get a bond in that material. It becomes very strong. All right. That now is what we have as plastic welding, and that's welding that we do without melting the material. But let's get into the region of welding now with a bigger volume. Let's suppose we want to look at gas welding for a moment. In gas welding, we're going to start off with something that we can get a very high temperature to. We're going to have to weld a very small packet of material, because joining means we're going to have weldment just at that particular point. And so we're going to have a very, very high energy source, high temperature energy source. And so if we look at this is what you start with in gas welding. I just show you this because I have a lot of trouble with this. You see, when I teach anybody to do gas welding, the first thing I have to do here is tell them about this little cylinder that we see here. And that's a cylinder that contains acetylene. And if we want to use an oxyacetylene flame, we got to have a tank of this stuff. And everybody that I have ever worked with so far, they tend to want to lay these things down, you know, so that if you have them sitting up and you knock them over, you can break off the stems, and you got rockets on your hands, you know, if you break off one of these under 2,000 pounds of pressure or something. So you're supposed to chain them up, chain them in a wall, put them in a special carrier, and another thing you can do is lay them down, and they can't fall over. And then they lay this one down too. But it turns out that acetylene is a very unusual material, and it's generally developed by the reaction of calcium carbide in water, and then we want to compress it, but we can't compress it to 2,000 pounds pressure. If you begin to compress acetylene, it'll explode. So you can only get it up to a few hundred pounds pressure. So what you do is take this cylinder and fill it up with something like Fuller's Earth or something that has a lot of surface area, and then you saturate that with acetylene, then you put saturate that with acetone, and then you put the acetylene under pressure over top of the acetone, and it dissolves the acetylene. And so if you turn your tank upside down or on the side, what you're really going to do is, by the gas flow, push the acetone out of the bottle, and you're not supposed to do that. Well, in any event, the problems we have with this are still more horrendous than that. And the problems that we're going to have with gas welding now are these. And let me tell it to you like a story that's a true story on a little consulting case I once upon a time did. And this has to do with a house in Washington that a lady moved in, and she liked to give parties, and she had a balcony inside the house that overlooked the entrance door, and she wanted to put a railing up. She wanted to put an aluminum railing up, in fact. And so someone went up and they welded little steel stanchions on at the bottom, and then they bolted on the aluminum balustrade up to on these particular parts. But there was a little weldment of a piece that went onto a stub that stuck into the concrete, a steel part. And this lady hired the company to come do it, and then it was all done, and it was finished in a hurry. And that particular night she came out and leaned against the balcony and greeting her guests, and the part broke and she fell. And so then there's a nice suit, and you go back and say, what's wrong? Well, we got the part, we got the welds. And here's what's wrong. If you take an oxyacetylene torch and you melt a piece of iron, just lay it on a brick in front of you and you melt it. You have molten iron. You've got a miniature open hearth furnace in your hand, right? And you have the source in your hand to supply all of the carbon that you want. All you got to do is make it a carbon-rich flame. Turn it up so it's carbon-rich. And the metal's going to sit there and drink the carbon up to 6.66%. And you can take a ductile steel and turn it into a brittle cast iron if you don't run the torch right. On the other hand, you say, well, I'm not going to get into that trouble. So you run an oxidizing flame. And if you sit there and play with it long enough with an oxidizing flame, you're going to generate iron oxide. And iron oxide is soluble in iron. And you can wind up with just a puddle of iron oxide, which is sort of like a high-temperature glue. It flows easy, it looks pretty nice. You can stick stuff together, but you got nothing, a very brittle material. It turned out that in this particular case, what the man had done was, it was a neophyte, someone wasn't used to gas welding, and he welded these joints up, and he used too rich in oxygen in the flame, and he put just loads of iron oxide in the weld itself. And so the weld, although it was there and joined the two pieces of material together, it was not like the parent material, and therefore it's not a good weld. And the definition of a good weld is going to be a weld which is exactly like the parent material and doesn't change the parent material.
Plastic or solid-state welding usually involves heating the metals to well below melting temperature and impacting the joint to drive out impurities. Oxyacetylene gas welding is widely used because of its convenience, but care must be exercised not to burn the flame too rich with oxygen or gas. A good weld produces a joint that's just like the parent metal and doesn't change the parent metal.